One of my absolute favorite problems in all of physics is the spring pendulum. This is where you take the pendulum that we've worked with before in Fun with Lagrangians, and you remove the string or rod or whatever you were using to hang the pendulum from, and you replace it with a spring. So now your pendulum bob is allowed to swing in an arc like it did before, but now the radius of that arc can change as the spring moves in and out, as it expands and contracts. So I've set that up here experimentally, where I have a mass hanging from a rod here. And actually I need to move my origin up to where the point of rotation is. So it looks like right about there-ish. And basically you let the thing go and you let it swing back and forth and oscillate in and out. I've got my calibration stick down here. So we are going to try to track this mass here, just to get an idea of what its motion looks like as it moves in those two kind of abstract dimensions. I like this problem because it's definitely two-dimensional, right? Because it has an angle and it has a length, but that length points in a different direction each time, but it's also always perpendicular to the direction it's moving in terms of the angle. So this is a great example of why you need cylindrical coordinates or polar coordinates as opposed to Cartesian X and Y. So let's open up our auto tracker here. So we will need to create a point mass. We're gonna call that point mass, what should we call it? Let's call it the pendulum bob. Here we go. And then we will auto track this thing. So that should be Control Shift Enter. And I think if I grab the pink, I should be in pretty good shape. It's the only pink thing in there. This week I added the green background for this thing so that it's more easily distinguished from the background. All right, let's click search to try this. All right, working well so far. Good, good, good. So there's three things you can watch here during this auto track. You can watch the actual trajectory to make sure that the dots are lining up on the thing itself. You can look at the template match to make sure that it doesn't suddenly become something in the background. And you can look at the trajectory, right? You don't necessarily know what the trajectory will look like beforehand, but you can usually tell when there's something jagged that happens. So this is working out well so far. So I think we'll put this next part in fast motion. Uh-oh, we have run into a slight problem here. Oh, shift click to mark manually. Okay, let's just do that then. All right, where are you looking is what I don't understand. I think you're looking up here, it looks like. All right, why don't we just hit Control Shift Enter once more. There we go. Okay, now the search box has come up. Okay, let's try that again. Search. Oops, and I did not realize I reached my hand in there, so we are going to walk this back just a few frames. We have plenty of data up there, so we will set the end frame slider to here. Okay, so that was a wonderful tracking session. If I look at the graph for just this initial look at X position versus time, I see it still oscillates, right? It still has to oscillate. It's two oscillating problems put together. The thing has to oscillate. I do see that the overall amplitude seems to die down, just like you would expect in a system with damping, like we have here with this air resistance. Let's check out the Y component versus time. Very similar stuff. Let's take a look at Y versus X. So this is a look at the trajectory. So this is, if you were to graph every single one of these points in real, physical, two-dimensional space over time, this is what the trajectory would look like. And this thing is absolutely gorgeous to a physicist. The things I notice about it is that it's pretty left-right symmetric, right? There's nothing special about this problem on the left side compared to the right side. And so I should expect it to be pretty symmetric about x equals 0. And lo and behold, it is, right? You could take this thing, fold it in half like this, and the left and right side would lie on top of each other. I don't see that for vertical, because there is a favored downward direction because of the Earth's gravitational field pulling this thing down. And so you notice I get some rounded corners here on the bottom, but much sharper corners here at the top. I also notice that I've got some interesting areas here in the middle where it keeps crisscrossing back and forth, whereas I have less dense areas in here, more dense areas, etc. So there are some areas where the pendulum bob tends to like to go, and then some areas it tends to spend a lot less of its time. I also see it looks like this thing never really repeats itself. And that's where it gets interesting, right? Because when you're looking at the pendulum, pendulums are nice, but once you see one cycle, you know how it's going to behave for the rest of eternity. Here, this pendulum crosses a different line. It does a different thing each time. Let's actually get a little bit bigger view here. Yeah. So we get this nice pretzel shape where these lines are never really crossing back over each other. And that's something that I hope we'll be able to see in our code as well. Now we could also look at the position magnitude versus time. So this is essentially the length of the spring, right? Because I put the 0 mark, I put the origin up here, and then I am basically measuring the distance from here to the mass, and so then that is giving me the length of the spring at that time. I can also look at the position angle. So you're looking at the spring problem individually, then you're looking at the angle problem individually, which is pretty cool. I can also look at those two opposite of each other. So I could look at the angle versus R. Let's actually do that the other way, because it looks like it's more symmetric going across this way. So we'll do R versus angle. And this thing looks really interesting because it's showing me that I can have, let's see, so a theta R of 90 degrees is right at where we are here, right where this thing is vertical. So think of this as sort of the rest position, and then as we go this way, we're rotating left and right from there. So I see it's left-right symmetric again. Again, not symmetric in terms of up and down, because it is a little bit easier, it looks like, for me to compress the thing than it is for me to stretch it. Okay, so this is actually flipped because longer is going to be this way going up, shorter is going to be this way going down. So that's really interesting. I also see I can't seem to get into this corner or this corner, right? So there's a little bit of maybe some conservation of energy going on there. Let's see. Let's take a look at our acceleration magnitude. Oh my, that's a hot mess right there. Acceleration magnitude versus time is, of course, going to be really messy because we're taking two derivatives by the time we get to acceleration. I could also look at the angular velocity versus time. I could also make a phase space plot of the angular velocity versus the angle here. And that's really interesting, right? So the vertical axis represents how fast it's swinging. The horizontal axis represents where it is in terms of its angular position. And here I've got this really interesting thing. You notice it can spiral out a little bit, but there's this circle in the middle where it can't go inside, right? It cannot go into there. Ordinarily at this point, I would show you the energy graph to try to get an idea of what's happening with the energies, but I did not record the mass of this hanger or the spring stiffness of the spring, and I have since returned them to the department supply room. So we'll just take this as sort of an almost picture of the conservation of energy. But again, what you can see is that you can't have both a small angle and a small omega, right? And you know that when it gets down to the bottom like this here, it has to be swinging past, or it has to be, it has to be stretching or compressing there, which is pretty cool. So anyway, like I said, this is one of my absolute favorite problems in physics. I'm looking forward to getting more into the Lagrangian and the modeling side of this with you in the next episode.